I've learned from
Just a couple
mistakes.
examples from, these are on number 6.
Six?
6, yeah.
Say it correctly.
And I'm gonna cover some trig stuff today. Your favorite.
From what?
Trig.
Trig? Oh.
Trig.
I thought you said trick, and I was like, trick?
Trig.
I like trick.
Okay. Look at those.
Look at them.
Look, behold. We're going to touch on 7 a bit too. You might have looked at 7 and gone, oh my goodness, those look terrifying, but there is a big hint to those, which I'll touch on here. Okay? This one. Okay? This is a, well, maybe you guys can tell me. What famous rule are we going to use on something like this? Yes, Alyssa. Lillian got it. Chain
I
rule.
was just thinking like L and X, which is just
A sticker.
X, right? But never mind.
Um,
No, it's okay. Just don't tell me I'm stupid. Just tell me I'm stupid.
Wait, hold
actually,
on.
I might have some stickers.
Really? Yes.
Are they dinosaurs?
Premium stickers.
Speakers.
I'll have to find them later. They're somewhere.
You're gonna.
Are they
Who wants to
gold
always
stars?
put stickers on our assignments?
Yeah, this is the chain rule.
Was this
So
in your-
the chain rule tells us that if we have a thing cubed, what's the derivative of thing cubed? 3 times that thing squared, and then we always tack on. Okay, so that's just one example of the chain rule. So for this one, we could say, well, y prime would be 3u squared times,
You prime.
what's the derivative of u? There you go. Painless.
Well.
Painless. Trenton? Boom. How do we feel about that?
I.
Gucci. Okay. Now, compare that to this one. This one's not a u to a power. It is another chain rule, though. This is also the chain rule. It's this type of chain rule. Log of u would turn into or if you like, I mean, u prime over u is a nice way to write that, right? Okay. So, now this one is a very sneaky answer to this one. Maybe someone is thinky winkies about it right now.
Probably not.
Jesse's out here.
Exactly.
We miss Jessie.
We do.
We miss you, Jessie. She's probably out there reading some mangas, right?
Honestly, I've only gotten her to read like one.
Naruto?
No.
Damn.
I think it was
Best
called.
one.
I think it's called Orange.
Oh, that one sucks.
Haven't read it. Couldn't
Okay.
tell you.
Yeah, it's not that good. Not as good as Harry Potter,
Oh.
of which I'm the foremost expert. Let the record show that I know more about Harry Potter than anyone.
And the name of the wind.
And what?
Name of the wind.
That's Kurt's favorite one.
Oh, and name,
Oh,
name
of
of the wind too. That one. It's a manga. Okay. So u is this thing.
Okay.
X to the what power?
1/3.
1/3 power. Okay. So, which by the way, that hint, if you're thinking sneaky, what's u prime?
Oh goodness.
1/3 x to the -2/3, right?
Yay!
Subtract 1 from the exponent. Okay, so that means that my derivative would be u prime times 1/u. Ugh, disgusting.
That
But
is
wait a
worth
second. Wait a second. Wait a second. Look at that. What's going on here? Who dat?
Oh. Hold on.
Well, it's a negative exponent, right?
Yeah, so.
So that's like 1 over x to the 2/3. Do we still see? You see? Wait a second, what's x to the 2/3 times x to the 1/3?
Okay. I was really,
How about that?
I was really second guessing myself there.
It feels me?
Oh.
Make sense?
Okay.
Now,
Yes.
does anyone see the sneaky way?
Not at all, no.
You take the.
Sneaky. Okay, so the sneaky way is
Put the
this.
1/3.
There is a
X on the
log
bottom.
property, which is that the log works in any base, but if you have x to the n power, that is equivalent to n times the log of x. Ring a bell?
Yes, Bell has wrong.
Any questions? Okay, so this one, what I could have done is I could have said, so I hope you would agree that that was not easy. Like that was a little involved. So what you really need to start doing is going, well, can I be a little clever here? Can I go like this? Start with that, and then go, well, I can manipulate my function before I take the derivative, right? And then from there, oh, wait a second. Now it's just a multiple of log x. It's making any sense.
Yeah.
Easier? Yes? All right. I'd like to show you a good example of how that can make life easier.
E?
Well, E you can't really do it on because that 5, we all understand the difference between like, I'm glad you pointed that out. So if you have log of x to the 5th, yes, that is the same as 5 times the log of x. But if you have the log of x to the 5th like that, that is not the same as that. Order of operations would be this thing, you go 5th power the x and then take the log of it. This one is you log of x and then you take the raise to the 5th power. Yes. So if you're doing a calculus on this thing, you got to treat this like a u to the 5th. That's how you got to treat that. Yeah. I was going to talk to you about like 7a.
Completely different
7A.
problem here.
Yeah. Well, all these questions are just, it's the same thing. It's just doing a chain rule, product rule, quotient rule with exponentials and logs. So we're going to talk about the derivative of this. And so when you first see that, you might go, oh, I got to do like a quotient rule inside a chain rule. But no, it's easier than that. That's right. There's a couple log properties. Well, there's really one that I want to focus on for this one. So we already talked about this one. The log of x to the n is equal to n times the log of x. There's another really famous one, which is that the log of a divided by b is equal to log of a minus the log of b. So how can I use that here to make life simpler?
You would just do natural log of x squared, subtract natural log of x squared plus 1.
Huh? So this can be actually written as the derivative of the log of x squared. Be careful, this is not the log of x squared, it's the log of x squared. Yes?
Yes.
Minus the log of Yeah. Cool beans.
Didn't you just do what you did on the previous problem? You just
Yeah.
take the 2 out.
Yeah. Now this one.
Yeah.
If I u prime over u this is my u, right? What's u prime over u going to be?
2 natural log x.
Oh yeah, you can actually you can pull the 2 out. Right?
That's what I meant by
That yeah, let's show how it works both ways. Yeah, because you could definitely, like Winslow says, pull the 2 out and get 2. It's 2 times 1 over x. But or you can just do u prime over u, so you get the same answer. So u
2x
prime
over
is
x.
2x over u, which does simplify to 2 over x, like Winslow said. And this guy, you can't pull the 2 out on this one because there's an addition inside. So you have to go.
Hello,
Greetings.
can I get Mr. Salmon and Mr. Taylor?
Okay.
You don't need to bring your stuff.
Okay.
Yeah. Honestly, nobody knows anymore.
This one's really worth mentioning. Something real quick, which is like if you looked at the domains, like I said before, it's not like a huge thing to worry about, but it's definitely relevant. What's the domain of this guy? Can x be a negative number here? Would it be okay for x to be negative?
Yeah.
Yeah, because you'd have a positive number. We know that you can log any number that's positive. The only thing x cannot be is a 0. That would be like the domain of this function. And then does this agree with that? Yeah, same domain. X can't be 0, so it's kind of nice. In this particular case, this wouldn't require any kind of domain restriction to be the true derivative of the other guy.
Oh, Mr. Hall. So why can't, kind of going back to the style we used for number 6. So the natural log of x squared plus 1, how come you can't just pull out that 2 in front? Is there,
Well, the property is this, right?
so there just can't be any constant attached to it then?
Well, okay, suppose I had the natural log of x plus 4 to the 5th power. Well, now you had that, you can see that this is of that form. I have a thing to a power.
Okay.
I could pull the 5 out.
Okay.
But that's not the same as if I have the log of x to the 5th plus 4. Well, now that does not have this form.
Okay, that makes sense.
Oh, why can't you cancel out the X on top of the second term?
This one?
Yeah.
Because
Plus one.
so suppose you want to divide the top by x and the bottom by x. And if you really wanted to, you could divide the top by, this is why maybe we should, by we, I mean like math educators should stop saying cancel out, because when you go from here to here, what you're really doing is dividing the top by x and the bottom by x. So suppose you wanted to do that here. You could divide the top by x, sure.
But then you'd have to put the 1 over.
You'd have that, which is fine, but. Okay. Feely report?
Okay.
Yeah.
Well,
Okay.
did you appreciate the things?
I want to cover some new stuff. I hope will be interesting for you.
Is this the trig stuff?
Yeah.
Okay.
Cool.
Oh, no.
I got to do attendance real quick. Why don't you try to do a couple of the ones that we just talked about, the ones that involve the log properties, and just make sure you understand them. And then we're gonna. Attendance. Mr. Trey's gone. No. Jesse's gone. No. Oh, you guys are already back. I thought they were gonna take you out. I thought they were gonna.
The wolf pack was on the hunt, okay, the street.
Was she questioning you about your patriotism? Because I didn't report you.
Oh,
Reported you last Monday.
Did I not say the pledge of allegiance last night that day?
You say the pledge of allegiance?
I didn't feel it.
You happened to be security. Anyway, I was gonna say it's when I did the announcement. Mm-hmm.
Apples are kind of amazing. How do they? This is crazy to think about what the structure of this thing.
Of an apple?
Yeah.
There's apple and seeds.
It's like candy just grew around.
Like about it.
Round seed.
You ever think about how a seed becomes a tree? That is insane. It's so small. You feel me? No?
Oh, I'm feeling.
You okay, Lillian?
I did. Can you simplify that?
All right, Lillian?
That's what I did originally.
Like if you cry every time.
About apples?
Today is April Fool's Day. There's been this surge of 10-year-old memes on the internet. It's been like really good. We've been seeing all these ancient memes come out.
It's been great.
They really bring me back to the good old days.
Chess.com put out an article.
Who?
Chess.com. About like the rules change. What was the
That's what I think.
getting rid of draws?
Is X over X just X?
That would be pretty funny. 'Cause a lot of
Getting
people-
rid of draws.
A lot of people do think there should be
Yeah,
draws.
I know. There was like an actual thing conversation. Like the first half, but I thought it was real. And then it talked about kicking each other's shins.
No, it's like, oh, okay.
A really good one would be like they talk about getting rid of the stalemate rule. So a lot of people really feel strongly that if you stalemate your opponent, it should be a win for you, not a draw.
Yeah, it had stalemates, draws, like king should take king or whatever. It was like all of it.
Well, then how do you do it properly?
The worst rule in chess is that you
How
can't
do you
cast
do
on
it
a check.
What's the rule?
But you can't cast on a check. It's stupid.
No, I get that. I mean, I can see why someone would be critical of that. I understand the people that are critical of the stalemate rule too, but anyway, okay. Do we want to like check an answer or two real quick before we move on?
Sure.
Like
Why not?
6A?
I got
6A?
Never mind.
It's just 3x squared over x cubed minus 5. I was thinking one of the more like challenging ones, like. Sorry. I didn't mean it like that. I'm sorry, Caleb. I didn't mean it like that. I just meant like one of the
Good job.
Let's do 7D.
D?
Yeah,
Oh,
let's do
yes.
7D. So
I concur.
Not that.
7D, you've got, you have log of a thing raised to a power. So
Hold on.
these can be tricky when you first look at them because you gotta go, you're kind of unwrapping
Oh, 7D.
the present. What's the first thing you can do if you're thinking of log properties? That 5 can get taken out.
Here.
Oh, not that far.
Not that. It goes way over.
And the reason you can do that is because it's of this form. It's log of, say, really I should write it like this, a to the b, because a could be a whole expression and b could be a whole expression. But if you can see it's in that form, the b can come out. So in this case, our a is this x over x plus 3, and our b is the 5. So the first step is just to say, I haven't done any derivatives yet. I've just rewritten it in this new form. And then what?
Could you do the?
Yep.
Yeah.
I've got a log of a over b, which becomes log of a minus log of b. So notice the 5 is being multiplied by this whole thing. So you have to use parentheses. Is that cool?
Yes.
Okay. And so now I'm finally ready to take the derivative. So does it make sense how the derivative of 5 times a function is just 5 times the derivative of that function?
Yeah.
So I can leave the 5 out here if I want. Derivative of log of x is 1 over x. And the derivative of, what's u prime?
One.
More than
One.
over x plus one.
There you go. So you might, I mean, maybe it looks nicer to write it as 5 over x minus 5 over x minus 3. Look at that. Oh, sorry, x plus 3. Sorry. There you go. You're done. Make sense?
Yeah.
Oh, good. Time to cover some interesting stuff. Were you saying ska and I oops? That was a good meme. We need to bring that one back. I love that one.
This dude won't hardly explain about
Dang it. Why not? What happened to them?
Society?
They got society?
Oh, yeah.
What did they turn into?
E-girls?
Yep.
You know, that's not wrong.
Okay, so the question is, what's the derivative of this? I will spare you the full proof would be involving the limit definition of the derivative. Pretty much everything in calculus, if you really want to prove that this is the derivative of this, you have to use the limit definition of the derivative. You guys remember that one? No.
Mm-mm.
Not the slide.
I remember that, but I don't remember standard deviation.
Oh, God.
What's there not to remember?
I don't know, formula?
That's the what class did you take that covered standard deviation?
Algebra 1 in HJ.
Me too.
Oh, yeah.
Full freaking formula.
Yeah.
What is standard deviation? I was in the same class.
That's a move.
It's the square root of the variance, bruh.
Bruh?
The square root of the variance is the expected value of x minus, well, your value minus the mean squared.
Oh,
Doesn't that
right.
sound fun?
So you have a set of values, and then you have the mean of those values, and you calculate the difference, how much does each number vary from the mean, you square all those values and add them up, and that's the variance. And then you square root the variance with standard deviation. Yeah. Okay,
Yeah.
this would be the limit definition of the derivative. So for this case, what you do is you'd say, okay, I guess you'd go sine of x plus h minus the sine of x over h, and you take the limit as h approaches 0, okay? You don't have to write this down. This is the hard way to do it. And this involves,
It's a
this
ball.
ends up taking you to you do a bunch of steps, you use a bunch of trig identities, you end up at a famous limit, and then you have to analyze that. It's like, in my opinion, it's outside the scope of a Calc 1 class. Maybe you might circle back and do the proof like this later in a Calc 2 class perhaps. But anyway, I'm just showing you, I'm just reminding you here, this is the limit definition of the derivative. And by the way, there are some questions like this on your problem set. Like, once we know what the derivative of that is, which I'm going to show you with sort of a hand-wavy argument, you'll be able to answer this question because you're going to know what the derivative is, right? Does that make sense?
Yeah.
All right. Quick review.
No.
Draw it better, sorry.
Oh, that's.
Yeah, still close enough.
No, it's not.
Okay.
Yeah.
This
I'll have
is
to check out that circle that Miss Marcus.
this is a unit. This is a circle. I'm going to make the radius 1. Oh no, it's the unit circle now. This is. I'm going to call the angle x because we're usually dealing with sine of x, and x is an angle.
Mhm.
How bigly is that quantity there? the horizontal value?
One times the sine.
1 times the cosine of the angle, and the vertical height is 1 times the sine of the angle.
Do we need to write this down?
If you don't already know this, then yeah. Like, hopefully you know this. If you've taken algebra 2 and pre-calculus and you don't know it, then
Still don't.
try to. There you go. It's there. It's there for you.
There.
SOHCAHTOA, just SOHCAHTOA. All right. The sine of the angle is opposite over hypotenuse. The cosine of the angle is adjacent over hypotenuse. And while we're at it, the tangent of the angle is opposite over adjacent. Okay. So some other really important things to know would be, what kind of unit do you use to describe these angles? Is it degrees? Pi. Radians.
Yeah.
How many radians are in a full circle?
2 pi.
2 pi. So this is 0. This would be 1 pi. What would this be then? Halfway, right? Half of pi.
It's all coming back.
And this is 3/2 of pi, okay? All right. So why am I drawing this? Well, because to understand why the derivative of this is what it is, the best way to do it, in my opinion, is to understand what the graphs look like. So what does the graph of this look like? Well, what's the sine value when your angle is 0? 0. What's the next time your sine value is going to be 0 if you move around the circle? Pi. When you hit pi. Okay, so here's pi.
Always gonna.
And then again, when you hit 2 pi. And then you see that it's periodic, meaning it's going to repeat, right? Once you go full circle, it's just going to do the same thing again, right? So whatever this graph looks like, it's going to do it again. Right? We've already seen this before, so it's like, okay, we know what it's going to look like. So the sine value, this height, is positive. It's a maximum. What's his max? 1. 1. So he's positive. It's a max of 1. Comes back down. Hits 0, and then he's negative. Right? So the graph's going to look like this. But he would then go forever, right? He would then continue on. Makes sense? Okay. So now, I'm going to look at the slopes real quick. So this is going to be y equals sine of x. Oh, shoot. Suppose I draw the slopes. Before we do this, let's actually draw the cosine graph too, because that's going to come up as well, right? We're going to talk about the derivative of cosine. Okay, his graph. What's cosine start off at?
0.
No.
1.
The cosine, the horizontal value of my point would be 1. So it starts off at 1. And when does it hit 0?
Pi and 3/2.
No, at half a pi. Okay, so if I put this is pi, and this is 2 pi, then my cosine hits 0. And then what kind of numbers are my cosines over here? They're negative numbers. So this graph actually hits 0 there. And then what's my cosine value when I hit pi? -1, which I have in my graph there. At least I tried to draw it good for you. And then it's going to circle around. Okay? And of course, the full graph goes forever and just repeats that pattern. This hopefully is ringing a bell for you. Okay. Okay. What kind of slopes do we have right there? Positive slope, right? And I'm going to just tell you the slope right there is 1. I know it looks kind of steep, but that's because this is 3.14 and this is 1. If I drew it to scale, you'd see that the slope there looks very much like 1. And what do my slopes do? When do my slopes hit 0?
At 1.
At half a pi. So my slopes start off positive, and then here's pi, here's 2 pi, I can see that my slopes, I hit a zero slope at half a pi. So slope is 0 at half pi, right? And then what do my slopes do?
Increase.
They go negative slopes, right? Negative slopes, negative slopes, negative slopes until when's the next time I hit a 0 slope? 3 halves pi. So my graph must do something like this. Make sense?
To a cosine.
And then I have positive slopes again until I get back to a similar point that I had before. There, my slope is 1 again. At 2 pi, the slope is 1, and I'm back to repeating. What's that graph look like?
Cosine.
It's the cosine graph.
Yes.
Okay. The only tricky part, well, I mean, this is obviously not a proof. This is just it is a sort of a loose argument for why this relationship exists. So, the moral of the story there is the derivative of the sine function is just the cosine function. Isn't that beautiful?
Yes.
Thanks, George. Thanks, fellow king.
Hello.
Okay, so this guy's friend, let's graph y prime over here. What do my slopes start off at? At 0, what's the slope of this graph? 0, starts off at 0. But then what do the slopes do as my x increases? What kind of slopes are those? They're negative slopes. And when do I hit so my slopes are negative, 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 and they hit 0 again at pi. So negative, 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 hit 0 at pi. Make sense?
Mhm.
And then what do they do here? They go positive, 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 until they hit 0 again at 2 pi. And of course, the graph would extend forever, but who dat? No, it looks like the sine graph, but flipped upside down, right? Negative sine. Okay. Moral of the story there is the derivative of the cosine function is the opposite of the sine function. It's negative sine. Okay. Feelies? How are the feelies?
Good.
Gucci Gang. That was a good song. Tour de force. All right.
It's a lyrical master.
Now you may
Truly.
be happy to know that is this graphical argument. That's all we got to use it for. From now on, we're going to use these two things as sort of like the atoms by which we're going to build up all the other famous results. So like, let's do tangent. What's the derivative? Maybe someone can think of what's the approach we can take to derive the derivative.
Well, you
That's
can
an epic
use
game moment
sine,
right there.
sine divided by cosine and just take.
What rule should I use here?
The quotient.
The quotient rule. So let's do that.
Let's do that.
What, Winslow?
That was new.
You said this is so lit. That's what you said, right?
Yes.
Yeah, exactly.
You said this is just like that feeling I get when I'm just Naruto running through a field. Feel the wind in my face.
You should do that in the drill.
No.
Can you imagine? It's like, hey, you're running. Yeah.
I'll be focused on my power.
Okay. This one, we got to be really careful on a question like this because it's going to be all a bunch of sines and cosines, which makes it confusing. Okay.
Yeah.
So remember your quotient rule is if you have, like, say, for example, f over g, that would turn into f prime g minus g prime f all over g squared. That's the quotient rule. So, should we list out the things like, I know
Yes,
some of you guys
please.
said you like to do that, so that's good. So this will be my F. This will be my G. Okay, so my F is sine of X. So what's F prime?
Cosine of that.
Cosine of X. My G is cosine of X. So G prime is
Negative sine X.
negative sine X. Okay? All right, let's just plug into the formula now. So, F prime G,
Whoa.
so what I did there? F prime times G. This maybe
Mm-hmm.
minus
We're gonna have room here.
G prime times F. There should be enough room, I think.
Oh, there it is.
Hopefully. It's not going to be like a massive algebra thing. It's a two-stepper. Maybe three steps. What's the bottom?
Cosine squared.
Cosine of X squared. Now we're going to go, can we do better? Let's see.
Yes, you gotta.
This top here is cosine squared plus sine squared.
Oh, yeah.
All right, this is the $1 million question. What is who dat?
Oh, is that?
No Ghostface Killer fans?
One.
One. Pythagorean theory. Remember that theory? The Pythagorean theory? It says that
Yeah.
cosine squared plus sine squared equals 1 squared. So this top here is the number 1. Okay. And then last thing, it's scary.
Is.
There's a hint here. If you look down, you're like, no, we have to do secant and cosecant again. Secant. No. Secant is the reciprocal of cosine, and cosecant is the reciprocal of sine.
That makes so much sense.
Huh?
That makes so much sense.
It does. It makes sense. You know where they come from is you take the unit circle and no, you put it, you, so like we already showed, this is your cosine, this is your sine, then you draw a tangent line like that. And then these segments, this segment, this segment, this segment, this segment, all correspond to your cotangent, your cosecant, your tangent, your secant, all that stuff. So, very interesting geometry. Right, fellow Zoomies?
Mhm.
Yeah.
Yeah. Okay, so this actually is secant squared. And there's a famous Quackmalus result, which is that the derivative of the tangent function is secant squared. Isn't that lovely?
Fascinating.
Is it?
Callie Joe, no? Callie Joe, you don't like it?
Jesse's arms would be waving and she'd be jumping in her
That's
chair.
sad.
She really would.
Yeah.
Miss you, Jesse.
Cool.
Press F in the chat for Jesse's absence.
It's so cool to this.
All right, guys. So let's do one more.
Let's not.
Oh,
No,
poor
let's
Lillian.
keep doing.
We're gonna do one more, and then tomorrow we'll finish them up.
Coolio.
We're gonna do the cosecant one. What's the derivative of cosecant? This is a little bit quicker.
1 over
Okay. Same thing, quotient rule question, because
Yeah, looks like it.
if I say, if y is the cosecant of x, that's the same as saying 1 over the sine of x. Let's use the quotient rule
So
again.
many letters,
What?
nothing. Your brain's just malfunctioning right now. Carry on, JL.
It's okay, Mr. Hall, I'm with you.
This is the f, this is the f, this is the g in this case. What's f prime then? When I use my quotient rule, what's f prime? 0. That's actually going to simplify life for us a little bit, right?
Yes.
0 times, so f prime times g minus, what's g prime? So this reads f prime g minus g prime f. Are we all comfortable with that?
Mhm.
And it all is over
Sin X.
sine of x squared. Now you kind of like, oh, that's nice. This whole thing is just nothing. So what I have is negative cosine of x over sine of x squared, and I'm writing it like that because capital T, they like to write this result as 1 over sine of x is cosecant of x. And cosine over sine, who remembers what cosine over sine is? Cotangent of x. And don't forget the negative sign. So they like to write the result like that. Not that it's wrong to say negative cosine x over sine squared of x, that is equivalent, but they just like to write it like that. Which is weird though, because look, he's showing up in his own derivative. Wow, what a savage. Right? Remember those movies? See how savage math is? You guys.
You did like a math YouTube tutorial channel